try to share my screen. So. Try this again. Met a couple of people. Here we go.
Usually I have my volleyball practice during this time, but today we are good to go. So I was actually able to join in today.
Excellent.
I'm sorry about that.
Okay.
I haven't watched every week though, like I was supposed to. And it's been
That's
really
okay. This is to have a kind of a graduate level class on a very specific topic. So I'm sure I'll do this again. But this was the tryout series. I just finished a book on this, so it's all a little raw and rough. But here we go. We'll start with second to last class on galaxy morphology, and I'll talk about galaxy evolution. So in principle, what a galaxy looks like is sort of the end product of all the evolutionary processes that shaped it. So if you're really ambitious, you go, well, can I track back why this galaxy looks like it does? And can I actually derive what happened to it for it to look like a disk with a galaxy with a bulge in the middle and a bar and streams around it and a certain globular cluster population? That is exceedingly ambitious, but you can definitely do it. You can definitely say things in a statistical sense, for example, about why galaxies look the way they do in the here and now, and why they look the way they do further out, and therefore more in the past. So this is lecture 6, morphology evolution. There's a lot to say about this, so I'm going to be brief in certain ways, but morphology, galaxy evolution is a very broad topic. It includes every kind of evolution. So I'll just try to focus on what happens to the morphology, what happens to the way galaxies look. And next week, I'll talk about the future of galaxy morphology. I'll talk about how I think we're going to do this in the future, what kind of techniques we'll end up using, what kind of surveys we'll end up using. But today we'll talk about evolution. So first, there are a couple of galaxy population relations. So there are things that we noticed in the local universe that seem to be hold for morphology or, for example, color or size. And the first thing to do then is to look back across cosmic times, to go look at more distant galaxies and see if those relations hold. We can also perform galaxy archaeology in the local universe. So that's something that we do we talked about last week about the low surface brightness universe, right? So those are the time scales in the outer parts of galaxies extremely long. So we look at those, and if that's a really long time scale, that means we need to, you kind of see a fossil. So you kind of see something that has mostly stayed coherent for a very long, like giga-years ago. And so we can do the same thing for the brighter parts of galaxies. We can actually pick them apart and look at a disk and say, okay, how many different generations of stars are in this disk? How many different generations of stars are in this bulge? And then the last thing we can do is basically throw everything in a supercomputer, take a cosmological volume, say, here, my physics, just kind of pour a whole bunch of hydrogen in there, watch it all turns into stars, and see what kind of galaxies you end up with. Along the way, you have to make a whole bunch of decisions. So you can see if you can tune your decisions, your prescriptions for how you turn gas into stars into galaxies into viable comparison to surveys. So you take like the Sloan Digital Sky Survey, you take a whole bunch of galaxies together and you compare these things across cosmological models, cosmological cosmological volumes for in both the survey and the model. So the first thing I want to say is that we definitely noticed a morphology density relation. So if you look at denser groups of galaxies, and especially a cluster like this one, you notice two things. All these galaxies are yellow, and all these galaxies are blobs. And it's not all of them. I see the occasional spiral galaxy just clinging on, but the vast majority of them are spheroidals, and they are yellow. So this is both the morphology density and the morphology color relation that was noted very early on. And so this holds true for high densities, right? So high density, you lose most of the spiral disks. The disks seem to be going away, and the cluster is mostly made up out of ellipticals and spheroidals, so S-zeros. So this was pointed out early, the Butch-Umbra effect. This is a modern version of this plot where you can see density on the x-axis and like a fraction of the different kinds of galaxies. And so elliptical galaxies at a low density, so on the left side, are only 10% of the population. And like most of the rest is, or like 90% of it is anything from a spiral. S plus I means spiral plus irregulars. So it's basically everything that's a disk. And S-zeros is something in between. So those are the three that they kept track of. And as you go to greater and greater densities, basically ellipticals become half the population if you are in an extremely dense environment, and then sort of like S-zeros are the other half, and there's like 5% of disk galaxies left. So clearly, if I move my galaxies into a denser environment, they lose their disks. So, chicken and the egg effect. Do I simply make ellipticals in dense environments, or do I turn spirals into ellipticals as I move them into a dense environment? And that's the latter is what we think happens. The spiral galaxies go into a cluster and basically get transformed into elliptical or spheroidal galaxies. So density, so the environment shapes galaxies. That's something that we can take away from this. So this holds true for all clusters. This is just happens to be one particular cluster. And so the next question is, does this actually hold for like lower density still, right? Does this hold for like groups of galaxies, or does this hold for the field? And the field basically, as you turn on the left, like the field of galaxies, basically as soon as you're outside the densest environments, then you still have 10% of ellipticals. That just seems to hold. But groups of galaxies do seem to pre-process galaxies a little bit before they fall in as a group into a cluster. So it seems to be, there's a quite complex relationship between density, between environment, and what galaxies look like. But there definitely is an effect. There's a correlation here, a very strong one. Now, the other thing that we noticed was that the more massive galaxies, so the x-axis this time is stellar mass that we estimated using a red filter or just a spectral energy distribution. More about that a little bit. And then we take a volume here, in this case, the gamma survey. And so we look at the different types. So we look at irregulars, we look at disk galaxies, we look at later type disk galaxies. I don't like the early late type distinction, mostly because I get it wrong all the time. But you got ellipticals, you got spheroidals, the S0 SAs, you've got the ones that are not bulge dominated, SAB, SACD, so the disk dominated ones, and SD and irregular, that's even, there's hardly any bulge at all. And so you notice that as a function of stellar mass, the ellipticals, they go all the way to like as big as galaxies get, like 10 to the 11.5. And irregulars, so the blue line, dominates the volume. So the volume density of these things is on the y-axis. So if you look at irregulars completely dominate around 10 to the 8, 10 to the 9 stellar mass. So if you have a small galaxy, odds are it's a irregular galaxy, or the light blue is the low surface brightness. So basically, if it's piddly and small, it is it's almost never an elliptical. There's like there's 100 times bigger chance that it's a regular or LSB galaxy. However, as we go to higher intermediate masses, we see that that's where all the disks live, right? So that's where the green and the purple lines are sort of, starting to contribute higher numbers of galaxies. And so, and at the end, you end up with ellipticals. That doesn't mean you don't have low mass ellipticals, quite the opposite, right? There's sort of like a constant density of these, somewhere between 10 to the 8 to 10 to the 11. So there's sort of like a flat line. There's a constant number density. So you have small ellipticals. They do exist, but relatively speaking, there's different contributions at different stellar masses. But if you have a really massive galaxy, your odds are that it's an elliptical. So if you're all the way at the end here, then it's those are all ellipticals. But as soon as you go a little bit down from that, there's already spiral galaxies, a few. And then if you're at 10 to the 10.5, that's where our Milky Way lives. Hey, look at that! Mm-hmm. It's full of spirals. Our Milky Way is a bog standard, most common disk galaxy, right? So it's SA. It's got a little bit of a bulge. It might be an SB. It's got a bit of a bar, so it's sort of like right at the top of that purple. And so these are called Schechter functions. If you want to look this up later, that's the functional shape that we're seeing here. Mm-hmm. And the reason that you see that they're a little fuzzy, those are that's the range of uncertainties in the fit. But what I wanted to show here is the fact that you have a total. That's that black line. Like if you add everything together. That's sort of the double Schechter fit that you need. But if you have individual populations, you only need one functional, one functional form. This is one third order polynomial, basically. So that's what you can fit to these things. So we noticed that there's a dependence on environment and there's a dependence on stellar mass. So these things know about each other. Okay, let's take that one step further. So Amanda Moffat, who visited, she broke it down in the following. Let's put everything that's a spheroid, so bulges, but also the whole elliptical and like spheroidal galaxies like S0s. S0s, it's all, it's all round, except for this tiny little disk. So let's subtract a tiny little disk. But if you decompose all the galaxies using Sirsic fits, you basically know how much of it is blob and how much of it is disk. And so on the orange side, on the left side here, you've got everything that's spheroidal, everything that's round. And you see that, you see the red line from earlier, that's all the spheroidal elliptical galaxies. But then you see that bulges actually contribute, like it follows the SB and the SC galaxies, right? Because that's where the bulges live, but they're a little offset to lower masses because they're only a fraction of that mass. And then you've got LSB galaxies, and LSB galaxies, not all of them are disks. So quite a number of them are simply, very faint blobs of stars that don't even form that many new stars anymore. So that is the light yellow there. And so this is sort of like all the things that live in randomized spheroidal, all the stars that live in spheroidal forms. And then you see that the total Schechter function actually sort of follows what the total is. And then you can do the same for disks and see where all the stellar mass for that lives in. And as you can see, just by the normalization, at the moment, more stars live in disky things than they do in spheroidal things, but they're getting there, right? So everything is moving from disks to spheroidals over time. We'll get to that in a little bit. But you can split that up, right? Because we think that there's something fundamentally different between stars that live in a disk because they're rotating, it's all organized, there's star formation going on, there's gas mixed in, so there's lots of gas physics happening. And in spheroidals, it's mostly pressure supported, meaning that the orbits are randomized. And so there's random orbits, they're all an isotherm, kinematically speaking, an isotherm blob of stars, and it's all orange, so it's all older stars just gradually evolving as stars with very little new star formation. So those are the two kind of galaxies that we think of, and that also seems to depend on the total stellar mass. Okay, so taking a different look at that, if you just look at a survey and you fit Sursic in these Sursic profiles, we talked about those in the second class. So we have a Sursic index, that's the, what the profile is. And we have the effective radius, the size of the galaxy. And then we can normalize everything by one filter. So what we do here is, these are RE, basically the X is the effective radius in a given filter, and REG is the effective radius in the G band, the Sloan Digital Sky Survey's G filter. And so the same with the NX is the Sursic index at a given filter, and NG is the G band. So that's our normalization. And you'll notice that depending on what kind of color the galaxies are, so we kind of can drop them in as like, oh, these are, broadly speaking, red galaxies, these are broadly speaking blue galaxies. And then there's also, is their Sursic index below 2.5 or above 2.5? And so you can see there's different relation between the ones that have a Sursic index above 2.5, those are spheroidal galaxies, and the ones that have below 2.5, those are disk galaxies. And they seem to have different dependencies between both the concentration, the kind of profile that they have, and the effective radius, the size that they are. So if we think about it a little further, it's like, hey, wait a minute, disks are blue and bulges are red. And bulges follow the Vauquelin profile, so they're very steep, and disks are, shallow, so they have an exponential profile. They have a very gradual profile. So if I go from a red filter, I'm just going to see bulge, and then it's like a concentrated profile that has a very small effective radius. And then as I gradually go to bluer and bluer filters, the disk becomes relatively more prominent, so my profile becomes shallower and wider. That's good to remember, because if we look at higher redshift galaxies, for example, we have to remember that those have intrinsically blue light because it's redshifted by the time it gets to us. So we see the star forming bits more prominently, and so we see disks more preferentially if we use the same color, but the disk is also dimmed. So actually the disk is the first thing to drop out, and we end up with only the spheroid. So if we're trying to measure sizes, we use that effective radius. So we go, okay, fine, we'll just pick a wavelength and we'll measure in those, right? We'll pick one filter and that's what we'll do it in. And so with mass, there's also a simple mass size relation. And this has been known for the last 2 decades or so. Disk galaxies do not follow a perfect little line there. Spheroidal galaxies do. So basically, I can scale up a spheroidal galaxy and just simply say, if I make it 10 times more massive, it also will be 10 times bigger in size. With disk galaxies, that seems to be not a linear relation. So the different slopes mean that if I want to compare to other, more distant populations of galaxies, I need to split those into disk and spheroidal galaxies. Otherwise, I can't compare them to local relationships. So people have been pointing that out and having splitting that up a few more ways. And so this is you kind of split it up in elliptical galaxies as zeros, SABs, and CDs. But I want you to notice one thing in the legend here. The SDSS is the Sloan Digital Sky Survey. So that's the local nearby Sloan survey of galaxies. And so those are images that's data. But the points are actually instances from the TNG, which illustrates the next generation. As you can imagine, there's quite a number of Star Trek fans in astronomy. And so we've named the Illustra survey, the Illustra simulations, which is one of those cosmological volume simulations. And this was the latest iteration of it, the next generation. And so they've made elliptical galaxies as zero galaxies and SBA and SCD galaxies, and they had sizes and masses because, it's just a computer entry. And so they can directly compare these to what we found from SDSS. And actually the comparison is pretty good. This is sort of where you expect them to be. There's some where you see the clouds sort of sashaying out of the color contour where you expect them to be, but it's not bad. You can also do the size relation. So you say, okay, I'm going to limit myself to one particular mass, and I should see that mass of galaxies, say the brightest galaxies, I should see them grow over time. So if I look at the most distant ones, redshift 10 is like as far as we can see with the Hubble Space Telescope, and then measure its size, because as it happens, you can actually watch that as they go to lower and lower redshifts, these things are bigger and bigger. I want you to notice here the scale of the y-axis for a moment. It goes up to 3 kiloparsecs. 3 kiloparsecs, our sun is, let's see if I remember correctly, 8 kiloparsecs off from the center of our Milky Way. And this whole galaxy is 3 kiloparsecs across. So at the very beginning, these galaxies were much, much, much smaller. If you look at the, this is in log space, so you have to convert for a minute, log 1 just means that it's 10 kiloparsecs. So typically these galaxies go much bigger in the local universe. And so in the early universe, you only see these itty bitty kind of small galaxies, but you see them get bigger as you go to lower redshifts. And so that uses the thing that gets us into look back time. And so as light travels with finite speed, that means that the galaxies that I see in the Hubble extremely deep field, this is one of the deep fields that Hubble has done over time. It simply picks a dark spot in our, we pick a relatively dark spot in the sky with as little stuff in the way, basically from our own Milky Way, and then stare with the Hubble. And then we look at these galaxies. There's about 10,000 of them in this field, and most of them are quite small, but those are from all the galaxies you see here are billions of light years away, multiple billions of light years away. And so I'm seeing the galaxies as they were billions of light years ago. That's a spheroidal galaxy, sure, but it's, 7 billion light years away, which means that I'm seeing it was a spheroidal 7 billion years ago. So I know that spheroidal galaxies existed 7 billion years ago. And so Hubble is a time machine, but only to the past. But the harder you stare at a patch of space, the more of these little things appear, and the further they often are. And so we can look at the colors, and we can match the light that from the time that it was emitted to local examples and compare if they look the same. Are they the same size, or do they follow the same mass size relation? So the trick to do that is to know the redshift essentially, and then match up the right filter. So top right, you see HST/F814W. That is science or Hubble speak for Hubble Space Telescope /filter 814 wide. And 814 means it's 814 nanometers. And that is the wavelength where you expect that's the peak wavelength where light comes into that filter. So the filter is a piece of colored glass that only allows light to arrive from between, and that the x-axis I put angstroms for, because I'm an optical astronomer mostly, and it goes from 7,000 to about 9 and a bit thousand angstroms. So if my light is in that wavelength regime, this piece of glass will let it through, right? So what it does, I flipped it up. If it's 1, it's completely blocking it. And if it's lower than that, it allows light through. On the bottom, I've plotted the same thing. So if it's 0, it doesn't let any light through. And if it's higher than that, it lets some light through. So those are the filter curves. These are things are called filter curves. For Sloan Digital Sky Survey, SDSS, U, G, R, I, and Z. And so these are the 5 filters that we've taken, a big chunk of sky, images of nearby galaxies. So if I take the SDSS-U filter, which kind of goes from 3,000 to 4,000 angstrom, so it's a lot bluer light, but I shift that out to higher redshift. So I shift that from 0 to 1. That light, the light that is locally seen in SDSS-U will actually be observed in redshift. If it comes from redshift 1, it'll actually have moved to the 814 filter. And SDSS-G is even better because basically, it sort of crosses that center line of the 814 at redshift 0.65, 0.67. So if I see a galaxy and I want to say, oh, cool, it's at somewhere between redshift 0.6 and 0.8, what should I compare my image to? And I should go to SDSS-G, one of the almost the bluest filter in Sloan. While I've observed it in what's effectively SDSS-I, right? So it's the same, it's very similar filter SDSS-I as it is to HST 814. So you have to remember that as galaxies are more distant, they are redshifted as the universe expands. So their light is redshifted by the expansion. So it was emitted in SDSS-G in a blue filter, but by the time it gets to us, it actually is in a red. It's a redder wavelength. It's a red wavelength. It's been moved to the red. So that's what we're doing below here. We've got this SDSS image, and then we've got redshift 0.85. So we've matched the right filter, so we can actually see. In this case, we're trying to mimic that effect by taking a blue filter and making it look like the galaxy, like it looks like at that redshift. So we make the pixels bigger, so it's a coarser image because it's further away. It's a little smooth a little because it's further away, and it's been redshifted because it was further away. So if you do that, and you can start looking back and see what kind of galaxy type dominated. At higher and higher redshifts, we see fewer and fewer spheroidal galaxies. Now, there was a fantastic set of papers back in 98, 99, right when the first Hubble Deep Field came out, because they said, oh, look, there are no spheroidal galaxies. There's no ellipticals in this deep field. Oh my gosh, spheroidal galaxies must have formed, in the last, since redshift 1, which is essentially the last 7 billion years. And so there's a whole bunch of learned papers about that. The problem was, of course, that it was a very small patch, and it just happened to miss spheroidal galaxies that were nearby. So it was an excellent example of observer bias. But we've done more of these Hubble Deep Fields, and definitely spheroidal galaxies popped out. So spheroidal elliptical galaxies have been around since redshift 3. That's almost 10 gig years ago. So the universe knows how to make elliptical galaxies early, and it's been at it for that most of that time. So, the fraction of them keeps growing because they're sort of the end stage, and the fraction of disk-like galaxies keeps diminishing. So disks are being turned into ellipticals. But if I look at that per volume, the number of disks seem to be, it does seem to diminish a little bit, but it's a lot more constant, but the number of ellipticals seem to be growing. What's happening? We keep making new elliptical galaxies. Sorry, we keep making new disk galaxies, so you can form new disk galaxies, and they turn into spheroidals over time, right? They turn into blobby galaxies over time. And that's that merger effect that we think is happening. Okay, so the other thing that you can do is look at more detailed things like, hey, when did bars in galaxies start to show up? So this is what Seth et al. In 2008 did. They used that technique where they matched things to Sloan images and then looked for bars in Sloan and looked for bars in Hubble images, and noticed that, bars, as you go further and further in redshift, the number of bars do seem to drop a little bit, right? So it goes from like most disk galaxies have, or a lot of disk galaxies have bars, to only a little less than half of them have bars. So the trick is you you can look for cosmic volumes. And so this is the galaxy, this is the evolution of the universe kind of plot where you say, well, on the left is time. So on the left, we start with the Big Bang. And as we go, the universe keeps expanding. And so if I want to look at the local universe, I have to look at a very large piece of sky, because then I have like the local comparison. But if I then go deeper, I can actually look at a smaller piece, but it's a similar volume. I have to match the volumes as well as I can, so that I'm comparing, enough volume of the universe, a representative chunk of the universe, both locally and at earlier epoch, and see if, what's the fraction of spheroidal galaxies? What's the fraction of disk galaxies? What's the fraction of bars, right? That's the kind of thing. That's what we use for look back time. What you can also do is simply model all the colors that you observe of the galaxies, and that's called a spectral energy distribution. So spectral as a function of the spectrum, how is energy coming off this object? And so model all the light from all the galaxies in one volume locally and in a volume at higher redshift and for longer ago. And so that's what happened here. Basically, they combined 3 different surveys. They combined a local survey called Gamma and Kids. I'm involved in that. And they combined a deeper look called Cosmos with 3D HST. So the good news here is that they actually plot look back time on the x-axis, and I'm very grateful for that, because I'm talking about evolution, and redshift, as you can see, doesn't actually linearly translate to look back time. If I'm at redshift 1, I'm about 7-8 gigayears ago, so that's 7-8 billion years ago. But if I go from redshift 1 to 2, I go from actually 8 billion years ago. I go from 8 billion years ago to 10.5 billion years ago. So the first step from 0 to 1 is 8 billion years. And then from 1 to 2 is 2.5 billion years. And from 2 to 3 is only 1 billion years. And from 3 to 5 is like also a billion years. So there's not a linear relation between redshift and look back time. So what we're really interested in is mostly redshift 0 to 3. That sort of covers most of the history of the universe. And so these 3 different Gamma, Cosmos, and the 3D HST sort of covered the redshift range with enough galaxies at each redshift at the whole look back time. And then you do these SED, the spectral energy distribution fits. So MagFizz is one of these pieces of code that does that. And so what it does is it trades light from the blue and says, all right, that has been reprocessed by dust, by the interstellar matter. So you lose blue light and it shows up again as submillimeter, so 100 micron light. Galaxies are essentially big blobs of stars and gas, and that gas has dust in it. And some of those have birth clouds, young stars, so lots of UV coming off them. And then the rest is sort of like intermediate ages, and everything gets a little bit reprocessed by dust. And you sort of balance the books where you have all the light, all the energy that's missing on the blue side explains how much you see at the 100 micron. So that near infrared, mid infrared, far infrared, and submillimeter emission from dust. So if you balance the books right, so this is what that looks like. So you have nearby galaxies, these are all from Gamma, and you see the red line is the model, the blue line is the model with no dust in it. So you can see that on the left-hand side, the blue light has disappeared, but the blue line is only the stellar emission, right? So that's the stars. And so they're mostly a black body function as soon as you get beyond 1,000 nanometers. So 1,000 nanometers is roughly visual. So that's where we are. That's what we look at. And then so that sort of drops off as a black body. On the blue end, more stuff is happening. So that's where the ultraviolet happens. And the ultraviolet is most affected by dust. So that's where the energy drops. And then pops back up as a second black body where the dust is. And so that's the trading relation that happens in an SED model. So sometimes you have So at the top, you have an edge-on spiral. So it misses a lot of its blue light because it all pops back out as dust emission. You see a face-on spiral. Okay, it's not missing as much of the blue light, so it's missing only a little bit, and that gets traded out as millimeter light. Then we see an elliptical, and the elliptical basically has no star formation. It has hardly any UV to begin with, and it hardly loses any as well. It just has, you see no difference between the model and the blue, the unextincted model. So the dust has almost zero effect, and you see this, you just see stars. What you see is what you get, and there's a little bit of dust emission left that's sort of like latently heated by the stars in there. And then you have like this complex little weird group, and then you get something like that. But you can do that as well to the higher redshift galaxies. Just everything has shifted up a little bit, but that doesn't matter. You've got a redshift, and so you can model the same thing, and you have all the same, if you have similar observations for these. And so you can say like, hey, hang on, that thing has, is laden with dust. That thing is booming with star formation. So you can actually model these things at all the different wavelengths. So what you then get is basically statistics on, you get dust mass as a function of stellar mass. So on the x-axis, we have stellar mass, except at the bottom, and then we have either dust mass or star formation. So this is the stellar star formation relation for all these different surveys. Even better, you can just do this as look back time. So you go for the last 12 gigayears. Well, let's be a little honest, about 10 gigayears is where we're complete. We can see values for star formation, stellar mass, and dust mass. And what I want you to notice is that all the different surveys sort of dovetail into each other. So if I'm looking at is my stellar mass between 10 to the 8 and 10 to the 11 and a half, right? That's where most of the galaxies that I see are. I've got those for all the way down to redshift, to look back time of 10, or a redshift of about 2, maybe even 3. Right, so I'm complete. I'm not missing any galaxies in that mass range, and I'm not missing any galaxies in that redshift range, meaning that I've got everything. I've got a full tally of the star formation. I've got a full tally of the stellar mass. Stellar mass and star formation have been accidentally switched there, sorry. So I've got a complete tally of both how much stars galaxies are forming in these different surveys, so as a function of look back time, and how much stellar mass they're holding. So I can say, okay, in this volume, I'm taking a random cubic megaparsec of volume of universe. How much stars are in there? How much star formation is happening 2 billion years ago in a cubic megaparsec of random universe? And so that's sort of what you get here. You get the densities as a function of, this is just to make sure that we actually understand how much is missing. But now you get those, you look at look back time. So you go as a function of time, how much star formation, so M-sol, solar masses per year per megaparsec. So this is the volume density of star formation over time. Now I want you to notice one thing. It's going down with, like, look back time from 10 gigayears ago was like the peak of star formation. For a given volume of our universe, the universe was making way more stars than it is now. About 10 times more stars were made per volume than there are now. Of course, the universe has expanded in that meantime, but at that time, the volume density was very high. So if you were a galaxy, you were forming stars rapidly at about 10 times faster than you are now, because the volume density was so much higher. And so that peak there is sort of like, this is a version of the Maddow plot. Maddow and Dickinson did a review of this, but this is basically the version of that. You can also look at the stellar mass, the stellar density. So it started at 12 billion years ago, with 10 to the 7 or even lower solar masses per megaparsec. And it just gradually grew because we made new stars, make new stars. And then it sort of the expansion rate of the universe and the rate that new stars were made sort of started balancing each other out. So it's been fairly flat for the last 7 or so billion years. And you can do the same thing for dust. Dust, on the other hand, is the one thing that gets destroyed. So stars, stellar mass, I mean, apart from the most massive stars, hangs around for a very long time. So you typically, I mean, our sun is going to be around for 10 giga years, so most of the width of this plot. So you lose some, you win some, but dust actually has a much shorter duty cycle. So as soon as you make dust, it basically gets destroyed as well. So it's fairly constant over time. Okay, so you have these evolutionary plots, and then you start matching those things to what people have done, modeling them in computers, but also just kind of much more simple with prescriptions. And so those are these lines where we actually try to match the evolution per volume of star formation, stellar mass, and then also dust. And the ultimate goal is that as you look back, can you actually get a reasonable tally of the different kinds of matter, the normal matter, right? What is it? 5% of the universe is normal matter. The rest is dark matter, so that doesn't tell us much because only the normal matter glows, so that's the only thing that we can really tally. But we know how much baryonic matter there has to be, and so which fraction is in stars, which fraction is in gas, which fraction is in dust, and we can actually see how that evolves over time. We all do that by looking at different volumes at different redshifts. So we try to match this up. So you see that you have data points as a function of look back time, as a function of redshift at the top. So that's one way to look at galaxy evolution. Now we do the second one, which is we only look at a nearby galaxy, but we say, okay, how old are the stars in its bulge? How old are the stars in the disk? How old are the stars in all the spheroidal galaxies? How old are the average stars in all the disk galaxies? So also an SED model, but an SED model that now kind of models the history of each galaxy as to explain the light that was coming out of it. And we can also pick apart morphological components. This is why we do this at low redshift, because we can actually resolve the galaxies better. So we can look at bulges, we can look at disks, we can look at even their low surface brightness components. So this is sort of an example. You get a model, and this is a galaxy on the top left, where we say this is the density, the surface density of dust. We actually model how much light these things get, what fraction of molecules they have. And so these are much more complicated SED models because they have much more information to work with. And so then again, try to explain this is the submillimeter bump of dust. So this is a dust focused paper, but you try to disentangle where the dust is, where the different kinds of stars are, and what the ages of stars are. A fantastic example of that is Sabine Belset's paper. She, once again, took the gamma survey, but now fitted SED models that included a star formation history. So when exactly did they form stars? And so you have a shape of the star formation history. It's all like everything formed 10 giga years ago, and then it just evolved passively. Or was it just a flat rate of star formation? Or was there a model, something like, did it ramp up or slow down? And so what you can see here is that she split everything in ellipticals, lenticulars, which is again as zeros, spirals, and irregulars. And so as you look at those, you can go, well, what's the star formation rate, right? So the star formation rate seems to decline. That's the top one. That goes down for all of them after 10 gig years. So redshift 2, 3 is when they all sort of peak. But the total is the black line. The ellipticals are the first one to sort of drop together with the lenticulars, but the spirals and the irregulars, they're not quite starting to drop as early as 2 or 3, redshift 2 or 3, or like basically 10, 12 years ago. What I want you also to notice is that the bottom one is, that's the stellar mass density. And so it marks when half the galaxy was made. And so you see that the lenticulars and the ellipticals, they made half their stars 10 gig years ago. So they had everything already 10 gig years ago, while spiral and irregular galaxies only, half their stars only got made 6 gig years ago. So as a whole, they're much younger in stellar population. You can also do that with individual galaxy and individual galaxy components. So this is an edge on S0 galaxy where we fitted the spectra of each. You see these little weird blobs that sort of like combined spectra. These are IFU data. IFU data takes a spectrum at each pixel. And so we have spectral information throughout this, double square on this galaxy. But you can get ages, you can get metallicity, you can get the iron over magnesium ratio, which is an indication of the kind of star formation, kind of stellar properties that is happening. So you can look at the different components. You can look at the thin disk, you can look at the thicker disk, you can look at the spheroid in the middle. You can, start parsing these things out. And then you get these things like individual morphological components get star formation history. So I look at the nucleus and it's got like its ages are like, there's some that got made between 6 and 12 gig years old. And then there's 2 more bursts around 4 and 1 about 1 gig a year ago. So there are 3 generations of stars in the nucleus. In the thin disks, it sort of has a more continuous star formation, but it was like a lot of star formation at the beginning. There's a peak at like 10 to the 10 gig years ago, and then it sort of declines to about 0 about now. And the inner thick disk and the outer thick disk also has like a double peak. So you can see like 2 things happened there. So, sorry, we can both look at a population of galaxies and model when they formed their stars, and we basically split them up in generally ellipticals, generally disks. Or we can look at individual galaxies and say, okay, when does this galaxy's disk form? When did its bulge form? Was there one burst or were there multiple bursts? Right. So the more information you get, the more look back you can do, and you can say this galaxy bears the scars of X and Y and Z. Right. So that's what you try to model. But then as a whole, and that's why the Belstead paper is so nice. These are the star formation densities, like look back, you can directly compare to what you see as you go deeper and deeper with Hubble and other surveys, right? So you can look what your archaeology, if that agrees with what, does your archaeology agree with your time machine? That's essentially what's happening here. And the cool thing is that they seem to agree in broader terms, absolutely. Yeah, we see the same thing. Star formation turns over between redshift 2 and 3. Spheroidals formed earlier than disks. We see that as this happens, that the star formation shut down in spheroidals first, and the disk still has it, right? So all this stuff is starting to neatly fall into place, that we have a broad picture of how galaxies evolved over time. Now, we have that broad picture, but what does that tell us about the physics? And so that's where it gets interesting, where we take a cosmological galaxy simulation, right? So we build this giant volume in a supercomputer. We start the initial cosmological conditions. Mostly that is a almost uniform distribution of hydrogen, in a little bit of helium, and the Big Bang has happened. You have an expanding cube of space, and it's almost uniformly filled with hydrogen, except that the dark matter has a little bit of overdensities and underdensities, and those start to contract. That's gravity. That's nice and easy with computers. But then you watch that hydrogen and that gas fall in, and that's where it gets interesting, because now you have gas physics, so you need to account for pressure. All that stuff has some kind of prescription how that gas then turns into stars, because it's completely pristine hydrogen and helium. So how does that actually compress into stars? What kind of population of stars? A lot of assumptions that go in there. But then you start to get stars, and those stars form into larger clumps, and those become galaxies. And eventually your computer cube arrives at redshift 0, arrives at the here and now, and so you can actually compare those things. And I think that's actually really clever, where we now can look at, hey, we're at a particular mass range. You know, what do the morphologies in Illustris on the left-hand side and SDSS Sloan on the right-hand side? So we can actually match these things up. It's like, how do they do? How do they look? I go like, oh yeah, okay, they get spheroids and they got disks at lower masses, all right, doing all right. We were seeing spiral structure, which is quite a trick because for a very long time, these cosmological pseudo-simulations did not have the resolution or the right prescriptions to make a disk and keep it. So it's starting to look very convincing that the Illustris galaxies, they have, especially if we put them through the same filters, we process them so that they should, we observe the emissions of, say, like, yeah, the star formation here in the disk. Then we take a spectrum of a young O star, for example, and then make sure that the right amounts of light in the right filters. So we're looking at the same kind of pictures, and they look very convincing. But we don't have to just squint at this, because there is an effect where our human eyes have a tendency to sort of confirmation bias, to go like, yeah, that looks exactly the same. We can do things where we actually do Searchlight profiles, like I alluded to earlier, or we can do things like morphometrics, what I talked about second or third class. And so these are morphometrics M20 and GD. And yeah, we see the pan stars, those are observed galaxies. So we see where the E0s and the SAs lie, we see where the disk galaxies lie, and we see where the mergers lie. And Illustris, TNG and Illustris seem to reproduce. Illustris struggled a little bit with enough ellipticals, but Illustris TNG seems to fill the same parameter space, puts its ellipticals where the ellipticals should go, puts the disk where the disk should go, and has a reasonable number of mergers going on. So I think this is very, this is very promising, where we seem to be getting our prescriptions right. And I want to make sure why I say prescriptions, it's because no matter how big if your cosmological volume is representative, it's very tricky to actually have all the small detail right, because suddenly, as the more detail you add, the finer the pixels, the bigger the file, and the longer it takes to compute. So the pixels within these galaxies are still several hundreds of thousands of stellar masses. So it's not like they are tracking individual stars in these things. It's more like they're tracking individual globular clusters, amounts of stars. And so there's a prescription where 10 to the 8, a little pixel of 10 to the 8 gas gets turned into a certain fraction of stars. And so that's, those physics are run with prescriptions, and those prescriptions can be tuned. But it's interesting to see that we are understanding what those prescriptions should look like pretty well now. I mean, we're getting quite a bit of detail from these new simulations where, yeah, you can actually tell whether gas is flowing in and flowing out, if it's a disk, if it's a rotating disk, if it's got a bulge or not. It seems to be getting a lot of the morphology right. So we have our different tools. So we have our scaling relations. We can look at scaling relations in the nearby universe and look at scaling relations at the higher and say, well, they look the same, or they're evolving with time. So we can look at distance. We can use distance as our time machine, not loop back, but look back time. And the rest frame wavelength means that we have to allow for proper comparison. So if we look at higher and higher redshifts, we have to look at bluer and bluer wavelength nearby to actually match them up. So use the look back time for populations, or we can model the galaxy archaeology of nearby populations. And so we have archaeology versus time machine. Both of them seem to agree. Do they match? And then we can compare both of those observational techniques to what we see from supercomputers, basically these volumes of galaxies that we simulate in computers, because there we can speed up the time. The one issue with galaxy evolution is that we have to match populations to map populations to populations. And so you can model, but their assumptions go into models. And so having a model that just simply runs through all of them, and we can just follow the same galaxy on its evolutionary track and see if it matches at different redshifts, and see if its end product actually matches what we see from archaeology. That's very, very useful. So it's looking quite promising for galaxy evolution, and especially for evolution of galaxy morphology. I'm starting to understand why we see more spheroidals at the distant universe, how they evolve, and we have a good chance of seeing, to understand how galaxies evolve a lot better, both how they look, but also what they're made of. All right. That's almost exactly an hour, which is what I was going for. So if anybody has questions, I'd love to answer some.
Thanks, Ben. Again, just a quick remark. When you talked about the star formation history that peaks at a redshift of 2, that's also the peak of the quasar density, and you can do the same thing with gamma ray bursts. So they really go together. Right.
So that's, I mean, I may have a bit of blinders on where I just look at how galaxies look and star formation, right? But it's quite interesting to see that you need to fuel your star formation. So the thing that we don't see here, sort of the behind the curtains, is where the gas is flowing in, if you're getting enough fuel to build new stars. And so if you have these two different techniques, archaeology and look back time, and they agree that, yeah, star formation peaked at this age, and you look at different techniques with like, yeah, that actually should also depend on how much fuel is coming into a galaxy. So like quasars should be switching on around that time, right? Because they, there's all this gas swirling around in dense disks. And so you can build a coherent picture. And the neat thing is that this sort of starts reinforcing itself where, I mean, we never would have thought to do this archaeology project if we hadn't gotten a hint from Hubble Deep Fields that, oh, look, star formation changes over time, like from redshift studies. But also now we have enough wavelength information on individual galaxies, or wavelength information on millions of galaxies, that we can start doing these kind of star formation history modeling. Like that was not possible when I got into astronomy. That was a complete pipe dream. Like, yeah, you can't do that. We don't have the information, we don't have the submillimeter information, and now we do. So it's quite interesting to see how that all fits together. There are going to be some issues, I think. I think dust is one of them. It shrouds things very effectively, and you don't know how it evolves with redshift very much, because all these models sort of assume the same disk with a thin layer of dust in the middle. If you start puffing that up, if it's much more turbulent, which I can imagine, if it's 10 times more star formation and 10 times more gas inflow, then you probably have way more turbulence in your disk. That might affect how things look, how things are calibrated. So we'll see how that goes. But in broad strokes, we seem to be getting a good picture here. Of course, there's the first galaxies, which I have left out so far because I've made it sound like we actually got all the way to the first galaxies, maybe implicitly. This picture does not include the very first galaxies. Redshift 10, I mean, we were at redshift 3, 4. That's sort of where we start with all these SED modeling, look back time, and what have you. Pushing beyond redshift 6 has proven to be extremely challenging. Our total sample of galaxies above redshift 9 is in the dozens. And so suddenly trying to evaluate how the universe is, how's the universe doing its job building new galaxies around the time when you only have like a dozen galaxies to work with, and they're probably the brightest things around, because anything fainter than that never made it into your survey. So this is why we're going to James Webb. I mean, I'm sort of winking at next week, because we don't have the initial conditions. We do not have the very first stars. We don't have the very first galaxies. And that will be very interesting. That's the reason why we're launching James Webb.
For these high redshift galaxies, are these photometric redshifts or are they spectroscopic?
Funny enough, the ones that you see here are all photometric, but we've been getting spectroscopic redshifts on these things using Keck. So basically take this tiny little blob on the sky and then stare at it with Keck for most of the night. And then you can see the Lyman alpha emission. And even better with ALMA. ALMA is actually seeing its ISM. And this is the other reason that you know that these are not the first galaxies, because they already have a dust ISM. They have carbon 158 micron emission. So there's already carbon in these galaxies. This is not the first generation of stars. This is already a little bit evolved.
Okay.
But yes, we have spectroscopic redshift confirmations of redshift 10 galaxies.
Wow, I wasn't aware of that. I thought the highest redshift, spectroscopic redshift, was our GRB, the 090423 burst, but apparently it's a galaxy, right?
It's a galaxy. The furthest known object at the moment is a redshift 11 Charism spectrum, but it also has been confirmed with ALMA.
Wow.
So ALMA is weirdly enough a redshift machine for this. It was conjecture whether or not these things would have enough interstellar matter to actually see with ALMA, because the conjecture is based on local analogs, but those are more evolved galaxies. So you sort of go, all right, we see this much star formation, so maybe it already has interstellar matter. Richard Bowens is leading the Rebels survey, and that just came out with a bunch of other new spectroscopic redshifts for these things. So yes, we know of the distance of about a dozen, but it is very, very hard to find these, and very, very hard to it's a struggle to do a single one. So it'll be very interesting to see what James Webb comes out with. But that's the point, right? The redshift 20 is only when the Big Bang. Well,
what?
Redshift 20 is where the dark ages are. So that's where we basically have our volume of hydrogen.
Right.
And so somewhere between redshift 20 and redshift 11 is where the first stars switch on. And so that's what James Webb is going to point at. That, and of course, is going to do lots of exoplanet work, but we're talking galaxies here. So, any other questions?
Thank you, Ben. I have to log off because I have another appointment right now. Okay, see you later. Bye.
2 o'clock. Bye. All right, talk to you later.